Sorry again. It seems that I was muted. Thank you for the comment from someone. Thanks for joining today for the session Top 5 Topics to Consider to Successfully Print with Peak. That we have a chance to still have a Formnext this year. So thank you everyone again for joining. I will discuss with you the top 5 topics that you should consider to successfully print with Peak. So first, I would make a short introduction about INTAMSYS. Our slogan is create infinite possibilities to customize our future. We are established in 2014 and headquartered in Shanghai in China. We are a world-leading company in innovative industrial FDM solutions, and we are providing end-to-end solutions from software, machine, materials, to give everything that is inside of the supply chain. We are the number one in Peak printers in the market, and we have a full portfolio starting with a 6,000 euro printer up to 100,000 euro. We have an experienced core team with a lot of members with more than 10 years in engineering, from metrology, electrical engineering, and so on and so on. We have worldwide sales. We have subsidiaries in EMEA, in Stuttgart, in Germany, and we have also one for the US, and for sure we have an office in Shanghai. Our solutions are targeted to aerospace, automotive, electronics, medical, R&D, and any other high-tech industries that require high-temp solutions. As I said, we see us as an end-to-end total solution supplier. So that starts with a process software, with our own slicer INTAMSYS, with our machine interface software INTAMTouch, with our own materials, with open material program, with certified third-party materials from well-known suppliers like Kimya, Polymaker, Huntsman, Victrex, Savic, and way more. And for sure, we have printers, high-temperature industrial printers, in every class that is required in the market. Now I will speak about the top 5 topics that you should consider. So first, it starts with drying of your filament. Drying of Peak is really, really necessary, and it's something that you must do. If not, you will have not success within printing. Even if you have a new spool, you should pre-dry it, as you don't know how dry the manufacturer put it, how dry it was when the manufacturer sealed the bag, and also a sealed bag is no guarantee to no moisture, as even the bags still let some moisture inside. We do recommend 5 hours at 150 degrees Celsius. We also recommend active dry chamber to keep the material dry within the print. So like slightly heated 70 degree or better 100 degree, depending a little bit on how long you want to print, and also on the conditions that you have in the environment. If you don't have this, you should place a sufficient amount of desiccant inside of the filament chamber to make sure that you avoid moisture uptake as much as you can. When you are finished with printing, take your filament out of the printer again, put it in a sealed bag with desiccant inside to avoid any moisture uptake as you can. And again, when you start with printing, even if it's only 2 or 3 days, re-dry the material. It will definitely take moisture up, and this has a big influence. And this is also what you see here on the pictures, that the material really starts to foam up. gives you a bed control within extrusion and also really less strength in the part. Topic number 2. Start with a good foundation, build plate treatment. So to have success within printing, especially with FFF technology, it's very important to have a good adhesion from your part to the build plate. So this is why we have a strict guide with a strict glue to say, okay, if you follow this glue, you have a good adhesion to avoid any failure. Due to expensive material, we do recommend to exactly follow this guide to not lose any gram of material. Gluing itself is very easy. You should apply 4 layers of glue. First, you clean the glass plate. Clean it only with water and soap. Don't clean it with special glass cleaners that may have a low-toss effect. This can be negative to the adhesion between glue and the glass plate. And then apply 4 layers of glue. Between these each 4 layers, you should wait 30 seconds to 1 minute that the glue has a chance to dry within this time. After this, your plate is ready for printing. And after printing and you remove the print, you can clean the plate again and repeat the step of coating with glue. To continue with topic number 2, we do recommend to print with a raft. For any parts that require a low to medium adhesion or that are printed with small nozzles like 0.25 millimeter. It's to print with a raft, to be honest, I'm not the biggest fan, but on PEAK it makes sense definitely. Due to crystallization that you can have within PEAK, you can have a bad adhesion, which is good to print with a raft. Later on, I will speak a little bit about layer adhesion, crystallization, and so on, and then you may understand it a little bit easier. The good thing here is when you print PEAK with a raft, you set the distance between the raft and the part to 0, which gives you a perfectly even surface on the first layer. You have no elephant foot, you have a good adhesion, and even on small nozzles where it's very hard to get a perfect build plate leveling, you have no issues within printing. The good thing here is you can play a little bit with the crystallization of the raft, which has a big influence on the adhesion between the raft and your part itself. It's very easy to keep in mind. A higher fan speed, the parameter is called raft top fan speed. A higher fan speed results in a lower crystallization, which gives you then a higher adhesion between the raft and your part. And on the other way around, a lower fan speed gives you a higher crystallization of the top layers from the raft, which gives you then a lower adhesion. In general, something between 0 and 30% is recommended, but this definitely depends on the geometry, on the nozzle size, and on the layer thickness from your part, and also on the layer thickness from your raft top layer, which is then again related to the nozzle size. So it's definitely not possible to give one value that works in every combination, but if you find one value for one combination, it works really, really good and very repeatable. One question that is definitely one of the most asked questions is, do I print amorphous or do I print semi-crystalline? So PEAK itself is a semi-crystalline polymer, which is very tough to print, which is mostly related to the semi-crystalline structure. PEAK has a very sharp crystallization point. So when you start to melt it, you break up the crystallized structures. And when it cools down, it crystallizes again. The problem that you have with semi-crystalline parts is that it's very hard to crystalline, to define when they crystalline or to have an influence when they crystalline. And this is the trick within amorphous printing. So when you print with amorphous strategy, you cool the parts a little bit down. You avoid too much heat in the part to make sure that the part do not crystallize. This gives you a good interlayer adhesion. You have a very good control about the crystallization, which results in a very low deformation and low internal stress, between each layers. If you see on the other hand, printing semi-crystalline, this again depends a lot on the parameters. How fast do you cool? How hot is your build chamber and so on, but gives you in general a little bit less interlayer adhesion, while it's very hard to get the crystallization on the point. And what you see on the breakage below is when you break the part, that really the layers split up. And this is related to the crystallization of the bottom layer. So the layer is already crystallized, and then you put a new amorphous layer on, which crystallize after a few seconds. And then you have two separately crystallized layers. They are not structured together. The point is, due to varying geometry, you have varying heat input on the part, which makes it very hard to control the crystallization perfectly. And this gives you in the end a higher risk of deformation due to internal stress. Also, with a heated chamber, with printing with a high heated chamber, you have the risk of overheating parts. So there's not only the risk of get the parts too weak, there's also the risk to overheat them and get small details very bad. Also, overhangs are worse. So our recommendation is to really go with amorphous printing. Why? Again, you have a very good control about the crystallization. That means you avoid the crystallization, which allows you still in the end to get a crystalline part. But if you then anneal it, so tempering or post-treatment, yeah, then you have a equal crystallized part. Overall, amorphous printing gives you a very good dimensional accuracy. So we speak about plus minus 200 micron. You have very good overhang capabilities. You can handle overhangs up to 60 degrees. And you have no risk of overheating parts. Even with very small nozzles on small parts, you get very good, detailed results. In the end, related to FFF-based technologies, so printing with a 0.25 millimeter nozzle, a detailed object in 1 by 1 by 1 centimeter is already very hard, related to the technology itself. If you then decide, okay, I will go with amorphous printing, and your print is finished, you should consider, when do you remove your part after completion? First, it's very easy to say, we do recommend to remove the part in a hot state. If you don't remove the part in the hot state, you have the risk that your part has more shrinkage than the glass ceramic. And when you then have still adhesion from your glue, you definitely get a lot of shear force. And in the end, you can get broken glass plates. So we do recommend to remove it in a hot state to avoid any high force to the surface of the glass plate, as the glass plate is very hard and slightly brittle. This is especially related to to the Delhi PVP glue that we do recommend, as the Delhi glue has still a high adhesion at low temperatures. Some other glues in the market, like Magigoo HD, which gives you a little bit less adhesion, they also lose their adhesion at lower temperatures. So there is less risk, but there's still a risk that your part has a too high adhesion to the build plate, and this results in a broken glass plate. And this is something that I would definitely avoid. As we print with amorphous strategy, we discuss a lot about do I need to anneal my peak parts? And there are 3 points that you need to ask yourself to know if you need to anneal or if you may not require that. The first is anneal your parts when the heat resistance above 150 degrees Celsius is required. If you have an amorphous part and you go above 150 degree, you have the risk that your part only slightly crystallize. You get deformation definitely, while you have no control how fast you heat it up and so on and so on. So this is definitely a maximum for amorphous parts. Second point, anneal your parts when you need to achieve the highest chemical resistance. Due to the increased density and the increased change of the chemical structure of the polymer structure, a crystallized part or annealed part has definitely less porosity in the structure, which gives you in the end a higher chemical resistance. Still, amorphous parts have a good chemical resistance, but definitely a little bit less than an annealed part, so a crystallized part. If you need the highest tensile strength of your parts, especially an X and Y axis, then you also should consider if you anneal your parts. If you, on the other hand, if you think about this and you say, okay, I don't need more than 150 degrees, I have no very hard chemical components that are touched by the peak part, and also the tensile strength of amorphous parts is good for me, then you could think about not anneal your parts. While this still gives you very good parts with perfect accuracy, and annealing itself is a process that gives you the risk of shrinkage in the part. It is also a process that costs more time and definitely more time and also money while you use gypsum or something. One thing is there quite important, and this is something that you see. I mean, I say, okay, higher than 150, high tensile strength. Let's see on the next page what's happened within crystallization or within annealing. So what you could see here is this is the structure, mostly how it looks when it's purely amorphous. So there's still slight crystallization, but this is more or less a very amorphous part. So you have a very open, chaotic structure. When you anneal it, the structure sorts, get more dense, and this is also the reason why the parts do shrink within annealing. You still see some amorphous structure, and this is related to the semi-crystalline, so to the semi-crystallinity of peak. So there will be not every time only one big block of crystallized structures. On the left, you see a bit more in values what you get out of amorphous parts and out of crystalline parts. So definitely the 150 degree on amorphous parts is the limit. On crystalline parts, it's 260 degree. The chemical resistance is better, and also the tensile strength and the flexural strength do rapidly increase, especially the tensile strength. If you look on the other hand to elongation, we don't have perfect values to share at the moment, but the elongation is way better. And the same is with the impact strength, that you have 19 kilojoule versus 10 kilojoule. So around 50% less than on amorphous parts. So if you go for jigs and fixtures, high precision machine automation jigs and fixtures, also amorphous peak can be a good idea. Yeah, while they are from the impact strength, while they are more resistant from the impact strength and still very stiff, and still have a high tensile strength of 65 megapascal, which is more than 50, 60%, 70% of all materials in FDM printing. One thing about annealing is definitely how to do annealing. And I have only one short slide for you. I could speak 2 hours about annealing, but what we mostly do, especially for sensitive structures, is to put the part in gypsum. So you mix up a gypsum slurry, put all parts within gypsum in a special container, dry this container, then heat it up first to 120, 150 degree, then you heat it up to 200 degree, then you cool it down to 150 degree, then you naturally cool it down to room temperature, and then you wash it out. If you look back, here is one curve how annealing look like. Especially the ramping is very important to get a consistent crystallinity. So slow ramping up and slow ramping down is very important for good annealed results. Yeah. For the top temperature, we use 200 degree, and as our start and finish temperature is 150 degree, as this is still a little bit below the HDT, so HDTA, where the part starts to get softened. Yeah. This is definitely a process that costs for one container, depending on part size and container size, minimum 1.5 to 2 hours. But it gives you the possibility to have a very equal shrinkage. There is still a shrinkage in the part due to change of the structure, but the parts are shrinking very equal, so you have no risk of deformation within gypsum. There are other ways within annealing without gypsum, but with sand or with salt, but in our opinion, they have a slight higher risk of deformation. So this depends also a little bit on your part geometry and also on your on the demand of your or on your requirements regarding accuracy of the part. Last but not least, I would like to give you a short introduction to our portfolio about our printers. It all starts with the Formnext HT, the first desktop printer which were able to print peak parts. It's a 6,000 euro printer, so very affordable to get first experience, first hands-on with printing high temperature materials like Ultim or Peak. Then we have the Formnext Pro 410, which is already a very industrial workshop-like machine with water cooling, dual extrusion, 7-inch touchscreen interface, over a filter in the chamber, heated chamber, and all these features that you require for high temperature printing. The Pro 410 is priced with around 25,000 euro. And then we have the Pro 610, which is our top machine with a big build volume from with 50 by 60 by 50 centimeters, and the build chamber up to 300 degree, and still an automatic material changer, heated material chamber, heated chamber, and so on and so on. And as we are focusing on industrial solutions, we have also a Flex 510, which is a printer which is mainly made to print elastomers on an industrial level within FFF printing. So this was everything from my side. I hope this presentation helped you to get an understanding how to print Peak, especially to have good success within printing Peak. I'm now open to get some questions of you, so please use the chat, write your questions, and let us try to answer them. If there are longer questions, please feel free to come later closer to me or my colleagues, Hao Yang, Bart Liffering. We are all on the Formnext, and we give you a warm welcome for a closer contact. So let us check some open questions. I think the annealing temperature is something that we already answered. So the Flex 510 is definitely only a elastomer machine. So it's not made for high temperature. elastomers. It's only made for classic elastomers, TPU, TPC, TPV, normal elastomers. So if you have a flex, if you have a Pro 410 as an example, which is a good machine for peak, printing depends on your part size, could be 3, 4, 6, 8 hours. And overall run within annealing, putting the part in gypsum, washing out, etc., takes roughly 2 to 3 days overall. Yeah, labor time itself is 1.5 to 2 hours, but especially drying costs a lot of time, and the ramping takes a lot of time. So around 40 hours is the shortest cycle that we do recommend. Another question that we have, is it the same process for ULTEM? So ULTEM is a purely amorphous material. You can anneal ULTEM, this is, but you don't get very big benefits out of ULTEM. Yeah, you don't get big benefits of annealing ULTEM. It only helps you to get less internal stress. This depends a little bit on the parts and on the machine that you use. Especially Pro 410 and HT, they have only a 90-degree chamber, where you definitely should anneal it when you want to get the maximum strength. If you have a Pro 610 HT, which has a 300-degree chamber, annealing of pi is not required. But definitely let us discuss this closer while in the personal conversation, while this is annealing ULTEM is a different discussion. We got another good question from Mike Block about geometry. So it's hard to give a perfect recommendation what kind of geometry is possible and what is not possible. What I could say is that with a 0.25 nozzle that we have for our machines, we can print wall sizes up to low to 0.5 or 0.75 millimeter. This depends a little bit on the requirements. Even thinner is possible, but then it gets less precisely. And it's a very good question, but there are more things than only wall sizes and holes. Holes itself or cavities inside of the parts are, especially with amorphous printing, very good handleable, while the material has a good overhang capability. We have one question about biocompatibility. In general, yes, there are biocompatible peak grades in the market. But this is something that is really definitely harder to answer. While it's not only about the material, it's more about the whole process. So that means your depending on the material medicine class that you want to reach, you need to get also a certification of your machine together with the material. So it's definitely not an answer where I can say easily yes. Justin Janis Krüger, please feel free to reach out later to some of us to give you a better answer, to also understand what you want to do. One question that we also got is chemical stability of these materials. So PEEK itself is very, very stable. There are only a few thermoplastic materials which are more chemical stable, but this is definitely something where you should look in detail. So chemical resistance is the question to what? Against acid, base, or whatever oils, and so on and so on. So chemical stable in general is hard to define. So please feel free to reach out to give a more precise answer on this. In general, yes, there are some materials, PVDF or PPS, which have also a very good chemical resistance, and maybe for some chemicals even more stable. What is about surface roughness? This is definitely a very good question. This is something that depends a lot on your application. In general, I do appreciate this question, well, especially when it comes to production. This is still a point that needs to be discussed. Yeah. One thing that you could do is you can use sandblasting. You can sand the parts. You can use a rotary tumbler to do some machine sanding, let's say so. Yeah. So definitely there are processes to reduce the surface roughness, but still it's FFF technology. So if you want to get the best surface finish, it's not the right technology. But then it's hard to get the same properties that you have with PEEK. So I see that we already had a lot of questions, and I tried to answer most of these questions in a short time. I can only ask again, please come closer to us if you have more questions. PEEK printing is not a very easy process, so this PEEK printing is definitely not an easy process, so feel free to reach out to come with your specific questions again to me or to my colleagues again. All of you will get, when you registered over our homepage for this session, will get a PDF of this presentation, so you will get somehow a recording. What I would like to do is to answer the last questions. What you have an idea about layer lines in PEEK? Do that have something to do with amorphous versus semi-crystalline layer printing, cause color difference? So one point, and this especially happens with semi-crystalline printing, is that different layers have different shrinkages, and this has a big influence on the bed surface. So what happens is when the nozzle, let's say your geometry changed from slice to slice, from layer to layer. That means you have a different crystallinity in each layer, and the different grade of crystallinity gives you a different shrinkage. And this really provokes a worse surface, and also makes layer lines more visible. So definitely printing amorphous and then anneal afterwards give you better surface results than trying to print in a semi-crystalline state. So again, thank you all for joining. If there are no open questions now, again, please feel free to contact us later on. We are here for Formnext. Thank you very much again for joining for this session.